So this video is for the second part of that handout on Taylor polynomials or Taylor series. And so, let's see here. Taylor series was the sum, k runs from 1 to infinity. So this is the kth derivative at a over k factorial times x minus a to the k power. Okay, and this second part of this handout is focused on quadratic approximating polynomials, so we'll call those P2 of x, and so that'll be f of a, f prime of a times x minus a to the first, and then f double prime of a over 2 times x minus a squared. All right, so let's see, problem 2. Well, the instructions for problems 1 through 6 say, find the quadratic approximating polynomial for the given function centered at the point A, and then graph the function and the approximating polynomial on the same set of axes so you can see whether or not you've got a good approximation. That's a good way to check your answer. So let's look at problem 2 here. So our function f of x is square root x, and our a value is equal to 9. So in a lot of the problems that we looked at in the previous video, we were working with a equal to 0. So in these, we'll have a not equal to 0. Let's see here. So the first derivative, f prime, is going to be 1/2 x to the minus 1/2, and then f double prime, negative 1/4 x to the minus 1.5. So f of a is going to be 3. F prime at a is going to be, let's see, this is going to be 1/2, and then a to the negative 1/2 power should be 1 over 3, so that would be 1/6. And then f double prime at 9, let's see here, that's going to be negative 1/4. And then, let's see, well, 9 to the negative 0.5, I believe, is 1 over 27. And so this is negative 1 over 108. And then our approximating polynomial will be, let's see here, that'll be 3, and then 1/6 times x minus 9, and then minus this 1 over 108 has to get multiplied by 1/2, so that's minus 1 over 216, x minus 9 all squared. Okay, so there is the approximating polynomial for that one, and let's take a look. So let's see, we want to look at square root x, and then also 3 plus 1/6 x minus 9 minus 1 over 216 x minus 9 squared. And let's see here, let's make our window, well, let's look at it in the standard window. So first let's look at it in the standard window, and then I will move to, let's see here. Let's see if we can get this graphed. Okay, so here it is in the standard window. Now remember that this approximation is best around the value for a, which in this case is 9. Okay, so let me change the window here. So I'll run the x minimum from 5 out to 15 here in the window. And that's just from hitting that window key right there next to the y equals. And now we'll graph this again and see what it looks like this time. So there's the square root function. and there's the quadratic approximating polynomial. Yeah, and so that looks pretty good. All right, let's see here. Let's look at another one. Problem 4. Some of that I should probably leave. All right. So, problem 4, our function is ln x. So, f prime is going to be 1 over x, and f double prime is going to be negative 1 over x squared. Let's see, our a value for problem 4 is equal to e. And so f of e, ln e is equal to 1. F prime of e is going to be 1 over e. And f double prime is going to be negative 1 over e squared. Okay, so quadratic approximating polynomial will be 1 plus 1 over e times x minus e minus 1 over 2e squared. Remember, you got to multiply that by a half, and then x minus e squared. Okay, so there's that one. Let's see what these look like here. Ln x, and then 1 over e, x minus e, and then 1 over 2e squared, x minus e squared. Okay, so let's look at these in the standard window and see what that looks like. Let's see here. There we go. And yeah, so I mean, it is a pretty good approximation. You can see right around where they're closest is right around between 2 and 3, and you know e is about 2.7, and so that looks like a pretty good approximator right around the value of e, but not so good once you start moving away from e. All right, that's problem 4. Let's look at problem 6. This. Move that out of the way. All right, so problem 6, our function is x sine x. So we're going to need the product rule to take derivatives here, right? And so our derivative will be 1 times sine x plus x times cosine x. And then our next derivative, a second derivative here, will be cosine x, and then we need the product rule on this one, 1 times cosine x, and then minus x times sine x. And let's see, what is our a value in problem 6? A is 0 in that one. Okay. So, let's see here. F of 0 is 0. F prime of 0, let's see, sine of 0 is 0. 0 times cosine is going to be 0 again. The only place in this one where we're going to get a coefficient is in the second derivative. Cosine 0, those are both 1. So we got 1 plus 1 here. This is 0, so that'll be 2. So our approximating polynomial is kind of disappointing. It's 0 plus 0 times x minus 0 plus 2 over 2 x minus 0 all squared. And so it's really just the parabola y equals x squared. Well, let's look and see what that looks like compared to the x sine x function. Let's see here, x sine x, and then is y equals x squared really a decent approximation for that? Let's see what it looks like. There's our x sine x function, and there's the parabola coming down. It actually is pretty good right around the value of x equals 0. So that's not a bad approximating function. Okay, let's see here. And I think I left that as number 4. Technically, that was actually number 6. All right. So that's it for those first 3 problems. Now on the bottom here, we want to find the quadratic approximating polynomial, and then use it to make an approximation, and then find the error by using our calculator to essentially get a better approximation. I mean, that's really all that's happening. I'll talk about that more as we go through these problems. But, you know, when we use our approximating polynomials that we've found, and then we test them against the values on the calculator really just has a better approximating polynomial. It has a longer one that's pre-programmed into it. So I've always, you know, kind of thought that was interesting, you know, that we look to the calculator to test our approximation, but all it's doing is just giving us a better approximation. All right, let's see. So problem 8, we've got this function 1 over 1 plus x. So that's 1 plus x to the negative 1 power. And we're using a equals 0. And we want to use this approximation to get a good approximation for 1 over 1.05. Now notice that when we do that approximation, our x value will be just the 0.05 part because we've already got the 1 right there. All right, let's see here. So f prime is going to be negative 1, 1 plus x to the negative 2. And then f double prime is going to be positive 2, 1 plus x to the negative 3. Okay, well with a being 0, that works out pretty nicely. So this will just be 1. F prime of 0 looks to be negative 1. And then f double prime at 0 looks to be positive 2. So our quadratic approximating polynomial is going to be 1 minus 1 times x minus 0, and then plus 2 over 2 x minus 0 all squared, or 1 minus x plus x squared. Okay, so there's our polynomial. Let's plug in 0.05, p2 of x, p2 of 0.05. So that's going to be 1 minus 0.05 plus 0.05 squared. Okay, so let's see. 0.05 plus 0.05 squared. And so this comes out to be 0.9525. 1 divided by 1.05 there. That's going to be 95238. So let's see, subtract 0.9525, and our error in this case is going to be 10 to the negative 4th times 1.2. Okay? So there it is. We're good up to the 10,000th place, which is a pretty good approximation, but it always depends on what you're using it for. All right, so that's problem 8. Look at problem 10. See here, problem 10, our function is cube root x. Our a value is 8, and we want to use that to approximate the cube root of 7.5. All right, so f prime is 1/3 x to the minus 2/3, and f double prime negative 2/9 x to the minus 5/3. Okay, let's see. So if A is 8. F of 8 is going to be 2, the cube root of 8. F prime for 8 is going to be 1/3 times 1 over 8 to the 2/3 power, which is going to be 4. So that's 1/12. And then F double prime for 8, negative 2/9 times, let's see here, 1 over 8 to the 5/3, so that's 32. And so this is negative 1 over 144. Now, if you're a person who really doesn't like fractions and you're using decimals for these, don't round them off, because a lot of these values are going to have some zeros as, well, let's see, 1 over 144 is 0.0069. So, be careful about how you round these off. This one is not so bad in particular. I suppose you could round that to 007. But just be careful, because if you round something in the tenths place, and you can see that our errors are showing up in the 10,000ths place, you're gonna throw off your approximation if you're rounding to the tenths or hundredths place. Okay, because our actual accuracy is going several places beyond that. So if you're going to round these off, be careful. Go at least past the point where the actual error is, and your calculator will turn these numbers into fractions, right? You could type in, if you're using decimals on this, just type in the decimal, then 8 to the negative 5/3, and then have the calculator turn it into a fraction for you. It's more exact, okay? You're less likely to lose accuracy. All right, let's see here. Let's wrap things up here. P2 of x is going to be 2 plus a 12th times x minus 8, and then minus 144 times a half, so 1 over 288, and then we'll have x minus 8 all squared. So, if we want P2 for 7.5, we'll plug in that 7.5 for the x. So notice now that we're actually kind of calculating this with a negative 0.5 in that place. Let's see here, negative 0.5 squared. All right, so let's see what this comes out to. So 2 plus 1/12 times negative 0.5, and then minus 1 over 288 times negative 0.5 squared. And so let's see what this comes out to be. 1.957, 465. And then the cube root of 7.5, let's see, cube root 7.5 is going to be 1.9574338. Okay, let's see here. So, minus cube root 7.5, oops. There we go, cube root 7.5. And so our error here is 10 to the negative 5th times 3, essentially. Okay, so in this one, our error is in the 100,000ths place. So that's what I'm saying, is that if you're going to be rounding some of these numbers and you like to do it to like the tenths or hundredths place, our accuracy is far past that. So please, if you're going to work with decimals, be very careful with that. Okay, I find it a lot easier to work with 1 over 288 rather than the decimal value 0.003472 repeating. This seems simpler to me, but there's nothing wrong with working with the decimals. But I know that people who work with decimals have a tendency to want to round them off, and in doing so, you can throw off how accurate our calculations actually are. Okay, so that's it for this handout, and I believe this is the last assignment for week 8, and these are due next Wednesday, which is the 27th. And then we'll have one more set of assignments that's due that first week in June, and then that'll be it. So enjoy your weekend. Bye.